All right, hi Algebra 2. Let's get this done. Lesson 19. Here we go. Hey y'all, this is the theorem that we're going to arrive at when we're done with this lesson. We're going to start off and tell you this is what it looks like, right? And it's going to make so much more sense once we get some examples done. We'll come back to it and look at it and see how it applies to these examples. So let's jump right in. Let's go ahead and do A. Let's divide f by x minus 2. And remember, we're talking about some function notation, right? So f, when we're saying f, we're talking about the function, or rather the expression, 3x squared plus 8x minus 4. All right, so when it says divide f by x minus 2, right? I could write this, right? But what is f of x, right? F of x is 3x squared plus 8x minus 4, right? And so what this is doing, when it says divide f by x minus 2, what it's telling me is to do this. It's telling me divide 3x squared plus 8x plus 4 by x minus 2. And so let's go ahead and do that. You know, for me, I really like synthetic division for this one. Since the coefficient of our denominator is 1 and our degree is 1, I'm good to go, right? So let's do that. So there's 3x squared plus 8x minus 4. Drop my 3 down. 2 times 3 is 6. 8 plus 6 is 14. 2 times 14 is 28. And negative 4 plus 28 is 24. There it is. Okay, so when we divide this, we get the result that this is equal to 3x plus 14, and my remainder is 24 over x minus 2. Fantastic. So we're going to actually arrive at something really interesting when we find f of 2. Remember, in our function notation, so I'm doing this down here, using our function notation, what does it mean? What does f of 2 mean? What that means is everywhere that you see an x in f of x, substitute a 2. All right, and if we calculate that, what are we going to get? Turns out to be 24. So we would say that f of 2 is equal to 24. Interesting, interesting. Do you see how this is our remainder? But there's something even cooler going on, and that is that this number, this f of 2, right? I got that from there. We're going to see a pattern start to form as we work through these examples. Okay, let's divide g by x plus 1. What does that mean? That means that I'm going to take what g of x is, this expression that is g of x, and divide it by x plus 1. Again, when I can use synthetic division, I will, because it's easier. It's going to save me so much time. And when you get quick at it, it really is efficient. Negative 1 times 1 is negative 1. Negative 3 plus negative 1 is negative 4. Negative 1 times negative 4 is positive 5. And 6 plus 5 is 11. Negative 1 times positive 11 is negative 22. And 8 plus negative 22 is negative 14. There we go. So we can say then that this is equal to x squared minus 4x plus 11. And my remainder is, right, it's a minus sign. Since my remainder is negative, I'm going to put a minus sign there. And then my remainder is negative 14 divided by x plus 1. All right, and I'm going to just do this one down here. So what is g of negative 1? G of negative 1. I'm going to plug negative 1 in for all of my values in g of x. Make sure I'm using g of x. Negative 1 cubed minus 3 times negative 1 squared plus 6 times negative 1 plus 8. Bam. And if we put that into our handy-dandy calculator and do some mental calculations, we wind up with g of negative 1 equal to negative 2. All right, do we see a pattern forming? Well, what happened? It's not fitting the pattern. Why? Because Mr. Dorman made a mistake. Somehow, I decided that negative 1 times negative 4 was 5. Perhaps it's been a long week. How about positive 4? So that becomes 10. This is negative 10, and then that's negative 2. And look, all right, cool. That's awesome, because these two, right, they should match. That's the pattern that we're starting to see, right? And then we're seeing that this is the opposite of that. Hey, I think we're starting to arrive at our remainder theorem. Sorry about the mistake. Here we go. Let's do another one. Let's divide h by x minus 3. So what we're being asked to do is to calculate x cubed plus 2x minus 3 divided by x minus 3. We're asked to find this quotient. Again, look, I can use synthetic division, so I'm going to. All right, so x cubed. So there's 1x cubed. There's no x squared, so I'm going to use a 0 as a placeholder. There is an x, that's 2, and then my negative 3 will go there. Drop my 1. 3 times 1 is going to be 3. 0 plus 3 is 3. 3 times 3 is 9. 2 plus 9 is 11. 3 times 11 is 33. And when I add those, I get 30, right? This is my remainder. So in other words, I can say that this is going to be equal to x squared plus 3x plus 11. My remainder is positive, and I'll write that as 30 divided by the quantity x minus 3. Okay, we imagine that the same thing is going to happen. Now that we formed this pattern, what do you think is going to happen when we plug 3 in for x, in h of x, right? In other words, what's going to happen, what is h of 3? Bet you anything it's 30, right? Okay, here we go. So let's look at h of 3. That's going to be 3 to the third power plus 2 to the third power minus 3. And I'm actually just going to go ahead and work this thing out. That's 27 plus 6 minus 3. Which is indeed 30. Fantastic. It looks like we've arrived at something here, right? That if we were asked, hey, what is the remainder of a quotient? Yeah? And we had, if our divisor is the kind that we could use synthetic division on. In other words, the coefficient of x is 1, and our degree is 1. I think we could probably plug in, right, the opposite of what's in our denominator. In other words, right, we could plug in positive 3, and we could just find our remainder. And that's essentially what the remainder theorem is telling us, just in much more succinct terms. So we also have a factor theorem, okay? It tells us that we can plug in a value for x, right? And if that value gives me a 0 in some factored form of a polynomial, then we wind up with something actually just going a little bit further. We wind up with an x-intercept, right? So we end up finding what are the zeros. What are the zeros? And if we find the zeros and we plug those in, we will wind up with our remainder. We'll apply that even further, right? We'll talk about zeros of a graph, okay? All right, so let's check this out. On a first look, this looks crazy, right? Talking about if x minus x plus 1 is a factor of p. Okay, what does that mean if x plus 1 is a factor of p? That means that x plus 1 divides this expression, x cubed plus kx squared plus x plus 6, evenly. It divides it in a way that there is no remainder, right? What happens, right? So remember, from our remainder theorem, we know that if we plug -1 into this, right? If we look at p of -1, oops, -1. Right? That would tell us what our remainder would be if we divided it by x plus 1, right? So what is this? That's -1 plus what? Just k, right? Because -1 times -1 is +1. And 1 times k is just k. So that's how I got that k there. And we have a -1 and a +6, okay? All right. Okay, let's go ahead and combine like terms here. So -1 plus -1 is -2. And we're going to add that to 6. So we'll wind up with 4 plus k. Okay, all right. So our remainder is 4 plus k. Kind of crazy, right? Okay, so remember, we said that if we do p of -1, that should be our remainder, right? Okay. But if x plus 1 is a factor of p, then our remainder should be 0, right? So shouldn't we get the case that p of -1 is 0? That's what we want. We would have liked this thing to be 0, yeah? Well, what we need to think to ourselves is, hey, what value of k will let this thing be 0, right? So, in other words, I want to solve this, right? So we said p of -1 is 4 plus k. And I want to know what value of k will let p of -1 be 0. Well, I can solve that, right? I can substitute 0 in for p of -1 here, right? And solve for k, not b. Let's go ahead and solve for k. And when we solve for k, right, subtracting 4 from both sides tells us that k is equal to -4. And we did it. Okay, in this question they're asking us to find two other factors. Let's go ahead and find at least one other factor. So in that case, what we're being asked to do is to divide, right? I want to divide p of x by our new expression with k equals 4 plugged in there, right? So in other words, in order to find another factor, well, let's go ahead and just write a negative here. -4 x squared plus x plus 6 divided by, so you wanted x plus 1, right? So x plus 1 is a factor of that, right? If we divide that, then we will be able to find our other factor. Here we go. Let's go ahead and do this division. Again, synthetic division is faster for me. -1 times -1 is -1. -4 plus -1 is -5. -1 times -5 is +5. This is a 6. -1 times -6 is -6. That's fantastic, right? If x plus 1 is a factor of my p of x, right? Then I should have a remainder of 0, which I do, which is fantastic. So I know that this is equal to x squared minus 5x plus 6, okay? In other words, I could also say that x cubed minus 4x squared plus x plus 6 is equal to, right, if we look at it in terms of multiplication instead of division, I have here the two factors of p of x are x plus 1 and x squared minus 5x plus 6. How do they get three factors? What they're doing is factoring our expression x squared minus 5x plus 6. And if you remember from your Algebra 1 class, this is factorable because there are two numbers such that if I multiply them, I get 6, but if I add them, I get -5. Those are going to be -6 and +1. My bad. No, they're not. How about 2 and 3? Sorry, there are some hooligans walking around in the hall. Distracting me. So how about -2 and -3? That's way better. So that's how you get the three factors. And later on in the course, everyone, we will practice our factoring again, just to get you back up to speed. I know you guys took geometry last year, so it's been a while since you've done some factoring. So don't freak out if that wasn't clearly evident to you. We're gonna make that something that you are. We're gonna reacquaint you with it later on. Alright, so here we're being asked, is 1 a 0 of this polynomial b? And what that means is, what they're asking is, hey, is this true? And let's see. And sorry, is 1 a 0? Sorry, I don't know. I was stuck on the. Oh, good grief! I was stuck on 0. is 1 a 0. So is p of 0, p of 1 equals a 0. Well, is that true? What's this? 1 plus 3 minus 28 minus 36 plus 144. And that should be 84. So then is p of 1 equal to 0? No, p of 1 is equal to 84. So my answer would be no. Hey, is x plus 3 one of the factors of p? In other words, if we divide p of x by x plus 3, do we get a remainder? Well, there are a few ways to figure that out, right? We could divide it, or we could use our remainder theorem, and we could say, okay, well, we could do this an easier way. I could see if p of negative 3 is equal to 0, right? So is that true? Let's see. What is p of negative 3? That is negative 3 to the 4th plus 3 times negative 3 to the 3rd minus 28 times negative 3 squared minus 36 times negative 3. I'm almost going to fit it in there. Plus 144. And let's calculate that bad boy right here. Okay, so if you put negative 3 to the 4th, and remember, if you're going to calculate negative 3 to the 4th in your calculator, put that negative 3 in parentheses, okay? Class is not over. So actually, this is going to become negative, or this is going to be this is going to be 3 times negative 27, right? Or negative 81, right? And then negative 28 times 9. So that's negative 252. And then 36, negative 36 times negative 3. So that's going to be positive 108. And then plus 144. Which turns out to be 0. Yes. Fantastic. So what's our answer then? Right? So in other words, there's no remainder when we, right? By plugging in negative 3, right? We have found that there is 0 remainder, right? By our remainder theorem. So if there's no remainder, then x plus 3 must be a factor. So we'll say yes. All right, so remember how I was talking about what the zeros were? It turns out that those are actually the points where the graph of these crosses the x-axis. We'll get into graphing these a lot more. This is going to be a very important tool, though, for graphing these things. So if we were to look at this, right, if it's asking us what the zeros are, it's also asking what are the x-intercepts. So let's look at it. What are our x-intercepts here? We're looking at, it looks like there's one here at 1, 2, 3, 4, 5, 6, so negative 6. And then there's one here at 1, 2, 3, negative 3. There's also one here at 1, 2, positive 2. And then also one here at 1, 2, 3, 4, positive 4. All right. What's really cool is that since those are zeros, I'm actually able to write this equation in factored form. It is going to look like this. P, right? It says it's a function P. So I can say P of x is equal to, and I'm going to put my zeros in, okay? So x plus 6. Now, why is it plus 6 instead of minus 6? The idea is that it's a 0 because if I plug negative 6 in for x, right, I get negative 6. Right, so if I was to plug that in for x, I get negative 6 minus 6, which is 0, right? And that's the point. If I plug my zeros in for x, I wind up getting a 0. And so we can continue this, right? We wind up with x plus 3. And then for our spots where this crosses the x-axis on the positive side, for positive values of x, I wind up with x minus 2 and x minus 4. And there it is. I was able to write that in factored form. Awesome, right? Not too bad. So look, this is a fifth degree polynomial. It has x-intercepts at -4, -2, 1, 3, and 5. And we can see that from the graph, right? -4, -2, 1, 3, and 5. There they are, right? Let's write a formula for a possible polynomial function that the graph represents. And we're going to use c as a constant vector because it's possible that there's some constant out there, c. Right, and when we're talking about c as a constant factor, right, a factor means that it multiplies it. So I'm going to call it our function f, so we'll call it f of x equal to, and c is just this constant factor, so that means that it's multiplied. And if I put it out in the front, it's going to multiply everything that comes after it. Alright, so this c is going to multiply everything in the parentheses that come after it. So let's put in our factors. So that would be x plus 4, right, because -4 is a 0, and then x plus 2. And we'll have x minus 1, x minus 3, and our last factor, x minus 5. And there it is. And see how that c is a constant factor? C is going to multiply everything in there, right? So that's how that comes out. And that is done. That is good. All right. What if our y-intercept is 4? Can we adjust our function to fit the y-intercept by finding the constant factor c? How would we go about doing such a thing? Alright, so let's answer this thing. What does that mean, the y-intercept is 4? Well, what are our coordinates of our y-intercept at that point? So if our y-intercept is 4, then we would have a coordinate. We would have the coordinates 0, -4, right? So let's go ahead and plug those in there, right? So f of x, so in other words, y is 4, right? Which is the same thing as, well, we could say that, right? We could say f of x equals y, right? We could say that, which means then, right, if this is y, then we could say that f of x is -4. So that's why I plugged that in here, and we're substituting that into our equation that we have here, right? So also x is 0, so we're going to substitute 0 as well. So I'm just doing this substitution step. So substitute that 0 in here. And lastly, right here, what do we wind up with? All right. So we'll go ahead and multiply that around. We've got 4 times 2 times -1 times -3 times -5, which is going to give me -120. So this is 4, and this is a -120c. All right, we just have to solve this for c by dividing both sides by -120, right? So what is that going to be, right? Well, let's write it like this. So let's write this 4 divided by 120. They're both negative, right? But we've got a negative divided by a negative, which is going to be a positive, right? So 4 divides 4 once, right? We're going to simplify this fraction. And 120 divided by 4 is going to give me 30. So that is the answer. Fantastic. Okay, so this is our lesson summary. So we're done with our video lesson for the day. Almost got it under a half an hour, but you've got all weekend to watch it. So thanks. Have a great weekend. Take care, guys.